Hello everybody, my name is Supoj Hengpraprohm. I am an assistant professor in Data Science program, Faculty of Science and Technology, Nagapathom Ratchapat University, Thailand. I would like to present in the topic of evolutionary computation in data classification problem. First of all, I would like to introduce my university, NPRU. Where is it?
NPRU is located in Hengpraprohm province in the center of Thailand. It is in southern of Bangkok, about 60 kilometers. We have 5 faculties, including Faculty of Education, Faculty of Science and Technology, Faculty of Humanities and Social Science, Faculty of Management Science, and Faculty of Nursing. We have students in bachelor degree, master degree, and PhD. The total number of students are about 15,000, and we have about 1,000 staffs here. That is the information of my university. Okay, let's move to my topic. There are 4 points to present, including what is evolution computation, how does it work, what is data classification task, and finally, how to apply evolutionary computation for data classification problems. Okay, let's see what is evolutionary computation. Evolutionary computation, or EC, is a family of algorithms for global optimization inspired by logical evolution. The subfield of artificial intelligence and soft computing studying these algorithms. In technical terms, they are a family of population-based trial and error problem solvers with a stochastic optimization character. Evolutionary computation techniques can produce highly optimized solutions in a wide range of problem settings, making them popular in computer science. Many variants and extensions exist, suited to more specific families of problems and data structures. There are 3 distinct interpretations of this idea started to be developed in 3 different phases. Evolutionary programming, or EP, was introduced by Lawrence J. Vogel in the US, while John Henry Holland called his method genetic algorithm, or GA. And the last one, Ingo Reichenberg and Hengpraprohm introduced evolutionary strategies, or ES, in Germany. These areas developed separately for about 15 years. Also, in the early 90s, a fourth stream following the general ideas has emerged, named genetic programming, or GP. Since the 1990s, nature-inspired algorithms are becoming an increasingly significant part of the evolutionary computation. EC techniques mostly involve meta-heuristic optimization algorithms. Broadly speaking, the field includes many techniques such as ant colony optimization, artificial immune system, artificial life, cultural algorithms, and the others. In this presentation, I will focus on 2 popular techniques, including genetic algorithm and genetic programming. The next one, I will show you how does the evolutionary computation work. Evolutionary computation is a computational intelligence technique inspired from natural evolution. An easy algorithm starts with creating a popula consisting of individuals that represent solutions to the problem. The first popula is created randomly. Individuals are evaluated with a fitness function, and the output of the function shows how well this individual solves or comes close to the solving the problem. If the termination criterion is met, the process stops. Otherwise, some operators inspired from natural evolution, such as reproduction, crossover, and mutation, are applied to individuals. Based on the fitness value of newly evolved individuals, a new population is generated. Because the population size has to be preserved as in nature, some individuals are eliminated. This process goes on until the termination criterion is met, reaching the number of generations defined is the most used criterion to stop the algorithm. The best individual with the highest fitness value is selected as the solution. There are various easy techniques such as genetic algorithms, genetic programming, and the others as I mentioned before. These techniques generally differ from each other based on how to represent the individuals. For example, GA represents the individual in the form of fixed length binary bit string, while GP uses tree structure. For example, this is the process of GP. Firstly, the initial solutions are created randomly in the form of tree structure. And then its solution is evaluated to determine its fitness by the fitness function. Next, a new population is created by using genetic operators such as reproduction, crossover, and mutation. About reproduction, a number of good solutions are selected to be reproduced to the next generation. This operator conserves good solution. Crossover operator recombines parts from two good solutions called parents to create new solution called offspring or child. Two good solutions are selected, and probability of a solution being selected is proportional to its fitness. The crossover points which determine the location to exchange parts are randomly selected. The subtree from parents are exchanged and creates two new offspring. The mutation operator changes some part of a solution randomly. A part is mutated by replacing it with a small random tree. While the process of GA, we just change the representation from tree structure to fixed length binary bit string. In crossover operator, a crossover point is chosen randomly from within the genes, and the offspring are created by exchanging the genes of parents among themselves until the crossover point is reached. Whereas mutation operator, some of the bits in the bit string can be flipped. These steps are repeated until the termination criterion is met. The termination criterion for the run may be defined by the best fitness value or a maximum number of generations. Throughout generations, the quality of solutions is improved. The result from each run is different as the search for a solution is probabilistic, and the solution is the problem is not unique. Now, let's see what is data classification task. Data classification belongs to the category of supervised learning in machine learning. It is process of predicting the class of given data points. Classes are sometimes called as targets, categories, or labels. Classification predictive modeling is the task of approximating a mapping function from input variables to discrete output variables. The classification algorithm utilizes some training data to understand how given input variables relate to the class and create the classifier. The classifier can be used to predict the class of an unknown new data. And now I will show how to apply evolutionary computation for data classification problem. In order to construct the GA-based classifier in our work, chromosome length is fixed to n. Each gene in the chromosome is the feature number in the training data set. In this case, we can use only numeric data. The chromosome is divided into two groups equally. To classify the data, the summation of feature values selected by GA in each group is calculated and compared between groups. If the summation of the first group is greater than the other, it is classified as class 1. Otherwise, it is classified as class 2. The total number of the correct classification is count and the fitness value of the expression. In GP, the solution is represented by a classification tree. The tree represented an arithmetic expression or logical expression. Let us call the classification by means of genetic programming as GPC or genetic programming classifier. In our research, we use the arithmetic expression. The tree consists of symbols from the function set f and the terminal set t. In our experiment, the function set comprises of arithmetic operators including plus, minus, multiply, and divide. And the terminal set T comprises of 10 constants, 0 to 9, and a number of variables. The variables represent the features. To evaluate the fitness of a candidate, its expression is evaluated. The variables are data from the training dataset. If the result of evaluating an expression is more than 0, it is classified as class 1. Otherwise, it is classified as class 2. The total number of the correct classification, denoted by C, is counted as the fitness value of the expression. The term 1 by size is included as the penalty for a large solution and to encourage a complex solution. The higher fitness value indicates the better solution. To test the model, we use 3 datasets of benchmark cancer microarray data, including lymphoma, leukemia, and colon cancer datasets. Lymphoma dataset comprises of 47 samples with 4,026 features. It is classified as 24 germinal century B-like or GC and 23 activated B-like or AC. Leukemia dataset comprises of 72 samples with 70,129 features. It is classified as 47 ALLs and 25 AMLs class. And colon cancer dataset comprises of 62 samples with 2,000 features. It is classified as 40 cancers and 22 normals. To evaluate the performance of a classifier, we use tenfold cross validation method. N records of data are divided into 10 groups equally. 9 groups are used as training set, and 1 group is used as the test. We exchange a test data through 10 groups and evaluate an expression in terms of its accuracy, defined as the equation. TP is the total number of affected subjects correctly classified. Tn is a total number of normal subjects correctly classified. And N is the total number of test cases. Due to the EC is a randomized algorithm, the experiment is repeated and the result is reported from the average of 10 runs. Using tenfold cross validation method, the total number of experiments in each dataset is 100. We compare the experimental results with many classifiers and feature selection technique reported in the published paper. The feature selection method are Pearson's and Spearman's correlation coefficient, denoted by PC and SC. ED is Euclidean distance. CC is cosine coefficient. IG is information gain. MI is mutual information, and SN is signal-to-noise ratio. The classifiers are multi-layer perceptron or MLP, k-nearest neighbor or KNN, support vector machine or SVM, and structure adaptive self-organizing map or SASOM. In the table, the values with highlight are better than the GA-based classifier. The comparison shows that the GA gives the better performance than other methods, about 80%, while the GP classifier yields a fair result comparing with others. Recently, the Ensemble methods have been proposed as a means to improve the classification accuracy. A number of classifiers which are different are used together, and their outputs are combined to give the result. The performance of the Ensemble approaches is significantly better than using any single classifier. In this scheme, the key of success is the variation of the member of Ensemble, and each member must provide a good performance. So we also proposed the way to create the diversity among classifiers by selecting and distributing different sets of features to different classifiers. Firstly, the features are clustered by k-means clustering method. The k-means clustering algorithm is a popular approach for finding clusters due to its simplicity of implementation and its fast execution. The algorithm of k-means starts with an initial partition with a fixed number of clusters, k. Then it assigns patterns to clusters in order to reduce the error between the data and clusters mean. After our data are assigned to clusters, the clusters means are recalculated and the process of assignment is repeated. The error tends to decrease as the number of iterations increase. The termination criterion is met if none of the cluster's members are changed, or the maximum number of iterations is reached. In this work, the maximum number of iterations is 10, and 30 clusters were used. After we apply k-means algorithms, the features which are similarly expressed will be grouped into the same cluster. Then, the features are ranked by SNR method. SNR, or signal-to-noise ratio, is a statistical method that measures the effectiveness of a feature in identifying a class out of another class. Many researchers reported that SNR feature selection provided the best result for classification. In the equation, mu1 and mu2 denote the mean expression level for the samples in class 1 and class 2 respectively. Sigma 1 and sigma 2 denote the standard deviation for the samples in each class. For each cluster in the ensemble I, select the ith best feature for SNR score of each cluster to form a set of features Si, and train the ith GPC by Si. After that, combine the output of all classifiers using the weighted voting approach, where each classifier I votes for its output with Wi. Ei is training error of classifier I, and Ti be the sum of SNR score of feature set Si. The class with the highest vote is the output of the ensemble. Using this method, each set of feature Si comprises of informative genes, but it differs from the other sets. The learning algorithm like GPC will be trained with different useful knowledge. As a result, there is diversity among the members of the ensemble of GPC because of the different set of features. The results suggest that the proposed ensemble GPC provide a good result, especially in the colon and lymphoma dataset. The proposed method provides the best result.
In conclusion, this presentation shows how to use evolutionary computation to data classification problems. There are many ways to improve the efficiency of the classification systems. In this presentation, I just show some research that we do. If you have any questions or comments, please send me your message and I will reply to you as soon as possible. Thank you for watching.